Okay, so I'm going to talk about left cosets. When we started this thing, here's my group G, or the set underneath the group. When we started, the cosets could have done anything. There could have been big ones, little ones, there might be overlaps, might have missed bits, there could be all sorts of peculiar shape, could have been any mess. But now we know something very specific. Well, we know lots of things. We know that the cosets are disjoint. We know that they cover all of G. Okay, disjoint and they cover all of G, and they're all the same size. Which is nice in the sense that there's a bijection between the two. So when we started, it was a complete mess, and now they're very, very much more regular. I'm not going to draw them in any kind of particular way, but they're all. I'm just trying to draw it in a reasonably sort of plausible way. That might be coset number 1, coset number 2, coset number 3, coset 4, and so forth. They're all the same size, and therefore they are an equivalence relation on the elements of G. Well, that's quite a powerful thing to say. And of course the equivalence relation is x is related to y if x and y are in the same coset. Okay. So if they're in the same coset, they're related. They're in the same coset there, and if x is here and y is here in another coset, then they're not related. So it's an equivalence relation, and also they're all the same size, and that tells us something quite profound. If we talk about GH, here's a new piece of notation. This is new notation. We say the index of H in G, which equals the number of cosets, can be left or right, the number of cosets in G, and they're all the same size. So that tells us that G colon H times the size of each coset, which is of course H colon 1, that's how you normally write it, that just means the size of H, that equals G colon 1. So this thing here, you can write it slightly differently. We say G colon H, which is the number of cosets, and of course the number of cosets of the identity element is just the size of G. So mod G, the number of elements in G, equals mod G colon H times mod H. Or we can say that mod H equals mod G over mod GH. Okay, and therefore the size of any subgroup divides the size of the group. Sometimes you say order instead of size, but it means the same. So for example, if we've got mod G equals, let's say, 12, then we know that subgroups must be of size 1 or 2 or 3 or 4. 5 doesn't go into 12, so it can't be that, or 6. I suppose this is or. Subgroup of size 5, subgroup of size 5 is impossible. Because the size of any subgroup divides the size of the group. It must be a divisor of it. Okay, this is called Lagrange's theorem, I think. Lagrange's theorem. The size of any subgroup divides the size of the group. But really what we're interested in is this relationship here, which all of which follows from the observation that the cosets of a group are an equivalence relation, or form an equivalence relation, and all the cosets are the same size. So that tells us it tells us a hell of a lot. How about a cyclic group of prime order? So how about addition modulo 13? So for example, 10 plus 7 equals 17 equals 4, all modulo. Because if you've got 17 divided by 13 and you've got 1 with 4 left over. So this forms a group, no subgroups. That's nice. If you have a group of prime order, well, nothing divides it. So there's, well, I say no subgroups. Of course, there's the whole group, and there's the identity element, which is there. But those are the only ones, because the only numbers that divide a prime number are the prime number itself and 1. This is called Lagrange's theorem, and I think it's really good. I'm going to stop there.